Thank you so much, Mark, for the kind introduction. I'm very happy to join you today. Although I wish I could join you for the animal visits and tours, and that would have been really fun, but really glad to be here. Um, as Mark mentioned, I'll be talking about some of the projects I've been doing, some old work and some new work. Hope they're interesting to you all. The first few slides are going to be likely very trivial for all of you in the classes that working on haptics, but I just wanted to kind of share the context of when I started my PhD. And the kind of motivation for starting this work. So when I was starting my PhD, it was a very exciting time. Even though AR, VR was around for a long time, the commercial devices were really taking off and people were purchasing them as a commercial device. And I always like to start with some applications of VR that go beyond entertainment and gaming, just to give some context for some of the applications I find most interesting outside of those domains. Specifically, I think VR is really excellent for doing things that you wouldn't have been able to otherwise, experiences that you couldn't have access to or would be too expensive or and not accessible. For example, you could experience what it's like to be on the International Space Station. Creating 3D artifacts, design lends itself nicely to virtual environments that are inherently 3D that take advantage of our innate spatial reasoning skills. And also, of course, learning. Here, I'm showing an example of someone exploring a 3D molecular structure, but there are also a lot of examples of training for professions that are very unsafe to kind of train people in the physical world. So you may want to do those trainings like surgical training or fire safety training in virtual environments first. And so when all these exciting VR devices were becoming commercially available, what was really missing was the sense of touch. So everything visually looked really exciting, but when it came to the sense of touch, as you know, a lot of these controllers that exist for commercial devices just kind of vibrated once in a while. And there was this really gap in the haptic rendering that was happening in these. And this is kind of what motivated my work as a PhD student. And when I think about how we interact with the physical world, we have these rich interactions where we feel the texture of materials, we feel the forces, and all of this allows us to improvise in our interaction with everyday objects. We pick objects, we feel their stiffness, their weight, and all of this allows for dexterous manipulation of these objects as well. So to address this gap that when we put on a VR headset and touch a virtual object, there's nothing physically there for us to feel and grasp and interact with. I was thinking at the time when I was a PhD student, it was a time where a lot of companies were working on drones. Drones were becoming smaller as well. They were being miniaturized and they were becoming more affordable. And so I was thinking, what if you had this swarm of drones that could kind of puppeteer your interactions with these physical objects and provide haptic sensation for you. So this is kind of the vision that I started off with as my first project as a PhD student at the time. And the idea was that could we predict what virtual object someone wanted to interact with? And as they would reach out to touch that object, one of these drones could fly around in the space and either look for a 3D printed object that was designed specifically for this application, or even an everyday object that resembled kind of the geometry and the properties of the virtual object that you were interacting with, so that when you touch the virtual object, you would have something to grasp and manipulate and receive the sense of haptic sensation. So I started off by kind of building the first version of the system. And my application domain that I was interested in was, for example, e-commerce. Imagine you wanted to shop in VR and you wanted to kind of feel the texture of the material and feel the weight of the fabric and all that. So this VR experience is quite a few years old now. So obviously the graphics are not as up to date, but you'll see throughout the presentation as we get closer to more recent work, things have come a long way from the graphics standpoint. But the idea was this in this virtual boutique experience, how could we provide the sense of touch, not just the force feedback, but the textures and the weight of the materials as well? So I started by implementing this with just one drone at first. So this is a custom racing quadcopter that we built, and I wrapped this in a lightweight mesh cage. This is a carbon fiber cage with a mesh around it to protect people from making contact with the propellers, and integrated this with the game engine, the virtual boutique experience that I showed you in the previous slide. And we were able to track the user's head, their hand, the drone, and whenever they were touching some object, we would send waypoints to the drone to automatically navigate and arrive there. So here is the video of me trying this experience, the virtual shopping experience. I can reach out and touch the scarf to feel the texture. And when I pick up the hanger, I can feel the weight of the material as well. So as you saw there, this sort of worked, but it didn't work great, right? There was a lot of movement in this drone. It was not very easy to make the drone go exactly where I wanted to go, and the drone was kind of shaky and moved around a lot. And this is not unique to this haptic system. A lot of haptic devices have limitations, whether it's handheld haptic devices, wearable devices, or this category of encounter type haptic devices, which are traditionally grounded robotic arms. But the drone could also be considered an encounter type haptic device because you encounter it when you touch a virtual object. All of these devices have some form of hardware limitation. And whether it's the accuracy of the haptic sensation they provide, the position of the haptic in this case, where the drone was having a hard time kind of being positioned precisely in space, or the speed at which they can move, or even the resolution if they're rendering some surface. So regardless of the type of haptic device, there will be some inherent limitation in the hardware, similar to the drone that you saw. And so the insight that I drew on in my work early on was that our perception as humans is not perfect. So we do not need these haptic devices to be perfect either. And to demonstrate this, even though I can't see a lot of you in the room, I'm just going to trust that you will do what I ask. But I'm going to ask that everyone touches their two index fingers above their head. You only get one shot and you can't look at your finger, right? So try to touch your two fingers. You get one shot. In my case, I can see myself in the Zoom, so I was cheating. But for all of you, um, whenever I ask people to do this, most of the room, the fingers are kind of crisscrossed, right? If you get one shot, it's really difficult to actually touch the end of your index finger without looking at it above your head. And this is because you're relying on your sense of proprioception, the forces in your arms and muscles that tell you where your finger is in space. And this is actually a very noisy signal. It doesn't give you a precise sense of where your finger, or more generally, your hand is in space, which is why this is kind of a difficult task. And most people in the room don't successfully complete it. I don't know how well people did there. And so this is what I mean by our perception is imperfect. And we can leverage this to actually create an illusion of improved performance. So make these haptic devices appear as if they work better than they actually do. So this is what I'm going to talk about today. The first half of my talk, I'll talk about some examples of haptic experiences in VR, where we leverage this idea that the limits of our perception to create an illusion that these devices work better than they do in order to address some of their inherent limitations. So in the case of the drone, the problem was that the accuracy of where it was positioned in space was not ideal. And I will also talk about another project where we use a shape display for haptics, and I'll talk more about that. And there, the problem is that the pins provide a low resolution surface. And so we were applying these illusions to create an illusion of improved resolution for these shape displays. In the second half of my talk, I'll shift gears a little bit and talk about kind of the context of robotics and AR, which is more about object-oriented interactions with robots. Haptic devices, in some ways, are robotic systems or hardwares that you're using. And here, instead of providing the sense of touch, they're actually physically manipulating objects. So it's not just the force feedback, but physically also manipulating. And so I will give you an example of how we apply this sort of illusory interactions to extend people's abilities using robotics and also provide explanations for what robots can and cannot do using augmented reality. So let's get started from the first project, the drone project that we talked about earlier. Um, the kind of goal of this project was to allow texture rendering. So we had these different fabrics attached to each side of the drone. And so depending on what object the user was touching, the drone would rotate and present the corresponding fabric to the user. We were also able to attach 3D printed props to the drone, in this case, a hanger, and simulate the weight of the object. And the drone itself also could act as a passive box. It could fly and land on different surfaces, and people could pick it up. And in the boutique experience, the shoe boxes were actually the drone itself. So some of you may be wondering at this point, would people even feel comfortable being this close to a drone? And this is what I was curious about. So before doing this project, actually, we ran a user study. This was an elicitation study. It was a between subject study design where we had half of the participants interact with a traditional drone without the meshed cage, and the other half were using an earlier prototype of our safe to touch drone. And in this elicitation study, we gave them a range of tasks. For example, they had to make the drones kind of fly up, land, move further, come closer, and all that. And we observed what kind of modalities they used to interact with the drone. And in the case without the cage, most people gestured or used voice commands to interact with the drone. But in the safe to touch cage, actually more than half of our participants physically grabbed the drone and pushed it around, picked it up, and used that as a way of kind of commanding the drone. So using direct touch interactions. So this was kind of encouraging that maybe with the meshed cage, at least some people feel comfortable being that close and having touch interactions with the drone. So going back to the problem that we were having with the drone, imagine you're kind of reaching out to touch a virtual object, in this case, this virtual fabric, right? This is the virtual hand, and that's the virtual fabric. Ideally, what I wanted in the system was for the drone to be positioned precisely where the user was about to touch. But as you saw in the video, the drone was sometimes a little offset, and more problematically, sometimes it drifted away. And so this was the problem that we wanted to address. And we drew inspiration from this Kai paper in 2016 around haptic retargeting. And if you've seen this work, it's a really cool magic trick. I don't know if anyone has tried this kind of retargeting method, but it's a very cool kind of magic trick that when you take off the headset, you're very surprised that there's only one physical cube there. So in order to apply this to a more dynamic system where the user is moving around and the endpoint, the target, and in this case, the drone, is also moving around, we had to kind of apply and understand how this works so that we can apply it to a more dynamic system. So in order to do that, we had to look at how the brain plans and controls movement. In this case, as you're reaching out to touch something, what happens in the brain is that your intent is sent, signals are sent to your body through motor commands, and this results in your arm moving forward. But the brain needs to have a way of kind of estimating what has happened in the world and how much progress has been made and what's going on. And it uses the sensory apparatus to estimate this. It uses the visual system to look at where your hand is in space. And as you saw earlier, it uses proprioception, the forces in your arms and muscles that also give information about where your hand is in space. So these sensory signals are then used to estimate how far your hand is moving and where it is currently. And then the difference is used to update the kind of motor command at kind of, you can think of it as every frame, and ultimately allow you to reach your end goal. So in the case of VR, what's interesting is that now you're putting a VR headset on your head, and VR is in a sense intercepting your sense of some of your sensory apparatus, right? For example, if you're completely wearing a VR headset that is not passed through, then we're kind of blocking all of your visual system. And so we can do things like track your hand and transform the rendering of your virtual avatar's hand. And that way, some of the sensory signals you're receiving, in this case, visual information, is coming from the virtual system. And some of the sensory information, like proprioception, is still coming from your physical body. But this allows us to kind of remap some of the sensory signals that you're receiving, in this case, your visual information. So going back to this dynamic retargeting that we were interested in applying, what we ended up doing is, as the user reached out to touch a target, if the drone shifted to the left, let's say, we would shift the user's virtual hand to the right. And as a result, their brain would try to kind of control for this and correct for this because of the discrepancy, and it will send the real hand further left to meet the drone where it is. And if this distance between the real and virtual hand were small enough, people wouldn't even notice that we were doing this. And what this allowed us to do is, even though the drone was not perfectly positioned in space, people were always able to make contact with it because ultimately they touched the drone where it was. And the reason this works is that you're getting information about where your hand is, both from your muscles, as you saw earlier, but also from your visual system. You're looking at your virtual hand. I'm not going to ask everyone to repeat the same task from earlier, but now instead of touching your fingers above your head, I'm going to ask everyone to touch your fingers in front of your eyes. You get another one shot. Okay, I see at least the virtual attendees are very successful in this task. This is a very simple task, right? It's easy. You can just look at your fingers and make sure they make contact. And this is because you're now relying on your sense vision, not your proprioception. And visual information is much less noisy, less uncertain. And your brain actually knows this. It knows that what it sees is more reliable than what it feels through proprioception. And so when there is a mismatch between these two sensory signals, it weighs your visual information over the proprioception. And this is known as the visual dominance effect. So this kind of illusion for doing this sort of dynamic retargeting works because of this. And we were able to use this and leverage this to overcome the challenges we had with the drone. So ultimately, we were able to run a user study. We had people come into our lab. They put on the VR headset. They tried this virtual shopping experience. They touched different fabrics, picked up different fabrics, and we saw that overall everyone was successful in the sense that they were ultimately able to receive all the haptic sensations we were hoping for. But we also found some limitations of this method. For example, if the speed of their hand was really fast, or if the distance to the target they were interested in was really small, then we weren't able to have enough time and space to gradually retarget their hand. And so in those cases, some participants reported feeling kind of like trying to navigate a really warped space, or ultimately had to try a few times before they really received the haptic sensation. Same with the velocity of the drone. If it drifted in the same direction and slowly, we were able to very gracefully and gradually add this retargeting. But if it moved around in different direction and really quickly, then again, it was not the best experience. So I'm going to just briefly mention a different project where we kind of extended this work by adding a predictive layer to mitigate some of these limitations. So in this project, led by Eric Gonzalez, we used a really small tabletop robot for haptics. So imagine you have a big control panel and you don't have access to such a large physical control panel, but you still want to be able to receive haptic sensations whenever you press a button or need to rotate a knob or kind of interact with any of the controls on the control panel. So we had the small robot that could move on the desktop to provide those haptic sensations. But the problem here was that the robot was pretty slow. So if the user moved really quickly from one end of the control panel to the other end, the robot couldn't quite catch up. So again, here we have a limitation of this haptic device, which is the speed of the robot. And we wanted to use these illusions, specifically the dynamic retargeting, to overcome this speed limitation. So what we did here was first, we predicted the target on the control panel that we're interested in by using a combination of their gaze and hand trajectory. And then we also predicted the estimated time for the hand to reach to that target. For this, we used a minimum jerk model, which is a well-studied kinematic model for goal-directed reach, which basically says that humans minimize the derivative of their hand's acceleration, which is jerk, during point-to-point reaching in motion. And we use that model to predict how long will it take for them to actually make contact with in this case, a button or a key on the control panel. And we also know the minimum or maximum speed of our robot, so we can estimate how far the robot can get during that time period. And now that we know this point of how close the robot can get to the target point, we can do a more graceful retargeting, where from the beginning, we retarget the user's hand to that point of reach, allowing them to make contact with the robot and receive haptics. And if the distance is really large, we kind of accept the fact that in those cases, that wouldn't be a good experience. And it's better to have a delay in how long they need to wait to receive the haptic sensation, as opposed to having to do a really large kind of retargeting. So this was kind of an example of a project where this predictive layer allowed us to kind of decide when these illusions were effective and when they weren't, in order to provide a better haptic experience. All right, so this was the first project where we used illusions to improve the accuracy, position accuracy of the drone. And in the second project that I want to talk about in this category, we were interested in using shape displays for haptics. I don't know if folks are familiar with shape displays, but basically they're matrices of actuated pins that can go up and down, and they can render these 2.5D surfaces, and they can also be used as a haptic device, another form of encounter type haptic device. But as you see here, the pins are not the smallest, which means the overall resolution of the shape display is not very large. And so as a result, in order to make high resolution shape displays, you have to miniaturize the motors that are attached to every pin, which overall increases the price of these haptic devices, and makes them kind of more complicated and expensive. And so we were interested to see, can we apply these illusions, again, perceptual illusions, to make these shape displays that are more affordable and low resolution appear as if they were higher resolution? So here you can see kind of me tracing this pentagon maze, and my finger almost gets caught in all these kind of angles because the pins are so large. I don't know if any of you, maybe everyone is too young for Microsoft Paint, but I remember when we would use Microsoft Paint and you would draw a line at an angle, it would be very pixelated. There was a rasterization problem. And so this is basically a rasterization problem on a kind of haptic device or shape display, where when you render a line at an angle, it becomes very kind of uneven. And so we were thinking of like, what is an equivalent of an anti-aliasing that you would do on a graphical user interface on a haptic device like this shape display? And what we came up with was applying something very similar to the dynamic retargeting, which is redirecting the finger. So again, we're moving the virtual finger up as the user touches the line, making them think that kind of that a control loop is not getting a feedback that the finger is not going the way it expected. And as a result, the uh, real finger ends up moving straight, whereas virtual finger is moving down. Sorry, I said that I think backwards. But the virtual hand is following a line at an angle that moves downwards, but physically they're just touching a horizontal line. And what this allowed us to do was achieve a very smooth linear path that didn't have this kind of rasterization problem. I'll briefly talk about some of the studies we ran with this because we were interested to see how far could we take this illusion before people noticed that we were doing it. You can imagine after a certain angle, people will really start to feel the forces in their wrist, that will give away the fact that there's a difference between the angle that they visually see their finger moving and their physical hand. So in order to do this, we ran a first study to determine this detection threshold for the angle. So this was a study where we did repeated trials. And so some trials didn't have any illusion. So the physical rendering matched the virtual rendering. And some of the trials, we were applying this redirection. So people were physically following a horizontal line while their finger virtually following a line at an angle. And what we were asking them was to tell us whether or not they thought there was an illusion. So it was there an illusion? Yes or no? And we did this many times across many angles. So we tried 5, 15, 25, 35, 45 degrees. And here you can see the angles that we tried. And on the y-axis, these are the ratios of repeated trials where participants said that they noticed an illusion when there was one. So this is kind of a classic psychophysics test where you get this S-shaped curve, where lower angles are less noticeable, and the higher the angle is, the more kind of percentage of trials participants report noticing the illusion. And the point of the kind of conservative detection threshold is at 50%. When people are really not sure, they're kind of guessing. Half the time they say yes, there was an illusion, half the time they say no. And in these types of studies, usually 75% is used as a point where most people, in most cases, notice the illusion. So in our study, this was around 49.5, which was surprising. We were expecting it to be lower. And what it meant was that almost all angles can either be mapped to a vertical line or horizontal line, because anything within the 45 degrees we could cover. And as a result, we could make almost all angles appear to work better than it did. And so we wanted to confirm this, so we ran a second study. In this study, we didn't tell people that there was an illusion or anything about an illusion. We told them we had two shape displays, even though we only had one, but they were in VR, so they couldn't actually see the shape display, so we could do this. And it was a method of two alternative forced choice task, the study, where they were experiencing one uh, trial with illusion and one without. And we were asking them which one they thought was higher resolution, what they preferred, and smoother to interact with. And so, again, we did this in repeated trials. And I'm going to report I'm going to share the highest angle we tried right below the detection threshold of 49 degrees. And we found that across our 19 participants and repeated trials, in most cases, most people preferred. I thought the case with the illusion was the higher resolution shape display, even though it was the same one, just with the kind of trick that we were using. They thought it was the one that was smoother and the one that they preferred to interact with. So this was kind of the takeaway was that even though we were using the same haptic device that had the same limitation, by applying this interaction and illusion to it, we were able to create a better haptic experience that was smoother and perceived as being higher resolution. I'm going to share another technique we tried. This was kind of like instead of a line, we were rendering a semisphere on the shape display. And as you can see, there are only a few pins within that area. So it's not a very smooth surface. My finger is getting caught on all these pins. And so what we ended up doing here is we blow up the rendering on the shape display and change the speed of the user's virtual finger. So if you're familiar with CD ratio gain on the computer mouse, on your Mac, for example, this is basically we're applying CD ratio gain to people's virtual fingers, allowing us to basically have larger renderings on the shape display, even though the virtual surface they're touching is fairly small. And so I'm going to skip kind of the results, but we did the same two studies again, and we found that within the scope of our shape display, we were able to increase the size of an object by almost 2 times without people noticing. And we got similar results where people basically said that they preferred the kind of enlarged haptic rendering over the original one in terms of their smoothness and resolution overall preference. So in this project, we kind of we're kind of dealing with another type of limitation of this hardware as a haptic device. And by applying these types of illusions that render the virtual hand at a slightly different place continuously, we were able to create experiences that were ultimately more uh, uh, better and smoother, and we were able to render more details on our shape display. Great. So this was kind of the end of the first half of my talk, where I talked about how we applied illusion to improve accuracy or resolution, or in the case of Reach Plus, the speed of haptic devices, even though the hardware still was inherently limited, the perception of those limitations were altered using the illusions that we were applying. Now, in the second half, I want to talk about a little bit more recent work from the past few years in my group at Princeton, and how we're thinking about interactions with robots more broadly and using augmented reality. So going from virtual spaces to kind of augmenting physical spaces where the robots are not just providing haptics, but physically manipulating objects. So the first project I want to share with you is Reality Promises, which we presented at the WIST conference last year. Um, and this was very much inspired by the go-go interaction technique from WIST many years ago. And this is an interaction technique where basically talks about how we don't have to be limited by the physical bodies that we have in virtual environments. We can, for example, extend our virtual arm as far as we need to grab distant objects that we wouldn't be able to in the physical world. And there are studies that have shown how far we can take this while people can still kind of maintain their control and grasp objects and manipulate them from afar. So we wanted to bring this go-go interaction technique to physical spaces, to the real world, not just VR. And we called it Reality Go-Go. And this is work done by my former postdoc, Mokari. Um, and this is my office actually in this video. And what he can do is basically reach out and touch a distant object like this chip and summon it. And the original one disappears. And now he has a virtual copy in his hand that he can place on any surface. Or you might imagine you're kind of sitting at your desk working on your virtual task, and you have a virtual panel of all the items in your fridge downstairs. And you can just grab the item you want, in this case, a coconut water, and place it on your desk and be able to drink from it. And of course, this is a case where haptics is not enough, right? Because it's not just about providing something I can grasp. I actually want to be able to drink the contents of this carton, the liquid inside. So I want it to be physically moved there, not just haptic feedback. And so what we do here is we call this a reality promise because there's almost like a fork between reality and virtual, what you visually see. And we have this countdown that, for example, after 50 seconds, this virtual carton of coconut water materializes. So it goes from being a virtual carton to a physical coconut water that you can grasp and not only receive haptics, but also drink from. So I'm going to show you behind the scenes of how this works. This is Mo sitting in my office. And of course, we don't have a fridge downstairs in my office, so it's just right there. But you can imagine this item could be somewhere else in an Amazon warehouse or downstairs in your fridge. And basically, the robot is fulfilling this reality promise and bringing the physical kind of coconut water to Mo. And to create this magical experience, we're actually kind of hiding the robot from view. I'm going to talk to you briefly about how we actually make this work in the backend. And there are two components to the system. One is what we call Skynet, which basically is the interaction synchronized robot control. And the other one we call Splatting, which is using Gaussian splatting to hide both objects and the robot from the view. So for the first one, we basically have this stretch robot in our lab that is integrated with the virtual system. And whenever the user issues a command, like placing an object, the state machine basically sends a waypoint, allowing the robot to pick up that object and fulfill the reality promise. And the second piece of it is on the rendering side. This is my office, and we basically use a regular iPhone to capture a Gaussian splat copy of my office. And this allows us to basically render patches of virtual renderings on top of the physical pass-through of the robot, allowing us to kind of have this experience where we can delete objects from view. So here, basically, we're rendering the Gaussian splat points behind the robot in front of it to hide it from view, kind of like an invisibility cloak. And once we do that, then we can feather the results so that the edges are more smooth, and do the same with the robot arm. And there, you can still kind of see it there, but you might imagine in the future with more accurate lighting and color matching, it would be less visible as well. By the way, if anyone in the class is interested in Gaussian splatting, we will be releasing a toolkit for Unity that allows you to do all these things really easily in a few months, probably a month or two, called Splat XR. So keep an eye out for that. So going back to the whole experience, basically what these two components allows us to do is have these magical experience where people can reach out, grasp objects, get a virtual twin that are relatively photorealistic, and manipulate them and place them in far surfaces. And again, the robot kind of fulfills the reality promise by moving the physical object and catching up reality to what the user visually sees. And here, the user is moving the object through this go-go reality interaction technique, but you can imagine there could be other causes too. For example, you can have virtual characters that now can actually physically move objects. So here, a bee can pick up a chip and bring it to you, and we have this motion path that almost distracts the user from the robot, and they meet at the same time. So once the bee places the chip, there's actually a physical chip for you to grab and eat from. So I'm not sure if folks are familiar with this really well-known quote, which is by Mark Weiser, saying that the most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they're indistinguishable from it. And I think we took a playful take on this and took it to an extreme where the technology, in this case the robot, is literally disappearing and invisible. But the kind of idea here is that there are new interaction techniques that are possible through XR in this space. And the last project I want to share with you is similar to reality promises, but kind of a more practical take, where maybe you have AR glasses that are not headsets with pass-through that can overwrite pixels in the world, but maybe you have a more lightweight AR glass where it's just adding virtual content to the world. And we can still have these object-oriented interactions for communicating with the robot and using it as a way to communicate to people what robots can and cannot do. So the first kind of projects I shared with you were VR. In VR, we were using VR headsets. Reality Promises was using headsets with pass-through augmented reality. And you can imagine some of these interactions could be taken to more lightweight AR glasses. And this is work done by my PhD student, Lauren. And the idea here is, I don't know if anyone has seen Mary Poppins, but that was kind of the inspiration, where maybe you can tidy up your room by doing direct manipulation and doing a lasso selection of objects and kind of snapping them back to their default position. And here we have these virtual twins of those objects generated. And unlike reality promises, we're not deleting the robot from view and we're not deleting the object from view, but you still get these benefits of direct manipulation with virtual content. And in the follow-up project, Lauren took this, extend this a little bit further, where the idea is now we want people to be able to understand the capabilities and the limitations of the robot through these direct manipulation interactions. And to do so, she basically created this model where the headset can capture the environment and have a virtual copy, which we call ghost objects. And also encode not only the kind of properties of these objects, but the capabilities of the robots in a fully simulated environment. And so with this, we were able to do things like this, where you can kind of grab an object and place it somewhere. And if it's possible for the robot to do it, you're able to kind of perform those actions. But if the robot, for example, cannot reach a shelf, you will be able to get that explanation in real time, allowing you to give kind of object-oriented commands to the robot within the range of its capabilities. And then you can imagine here, Lauren is in the same room, but you can imagine this could be done for teleoperation in spaces that you're not physically present in. Another example for multi-object interaction, again, you can kind of lasso select multiple objects and their virtual twins, and you can either snap them to their default location or place them elsewhere. And when there is an issue or limitation, you can either ask the robot to suggest an alternative, or you can kind of um, ask the robot to try something, or you can virtually or physically help the robot. And this is what kind of the user study for this paper was focused on, understanding when and how people, and whether or not they can figure out how to help robots when they needed it. And then the last example, which goes beyond pick and place, is interacting, for example, with this curtain. And so here, there's a rod on the left side here that's blocked by the chair, and there's another draw over here. So this one opens the gaps, this one pulls it up, and of course the robot can't reach there. And this is what, if you kind of select the curtain, you can pick the action. So the action possibilities are surfaced through augmented reality, but you can see why certain actions are not possible. And so you can pick the ones that the robot can do. And you can specify the spatial parameter, in this case, the height of the curtain, um, with direct manipulation. And once you send the commands, the robot fulfills those commands. And of course, we have a lot of kind of future work in the space that we are interested in. We want to expand our simulation to create all these virtual models and environments on the fly, as opposed to reconstructing them beforehand. We want to expand this to remote teleoperation settings. And we're also interested in exploring robot learning, where through these interactions, the robot can learn user preferences over time. So today I talked to you about these 4 projects, 2 of them using illusory interactions for haptics in VR, and the other 2 using augmented reality for interacting with robots. And by no means, I mean, I think that we should always interact with objects, as opposed to directly interacting with the robot. But I do think that there are complementary interaction paradigms where maybe some interaction, it makes sense to work with the duplicates in XR, and sometimes we may want to directly communicate with the robot through gestures or language and things like that. And even then, I think there are opportunities for XR to help us. For example, if there's ambiguity in the instruction, when I say, for example, can you fetch me that thing? We can use AR to communicate the uncertainty and help people disambiguate as they communicate directly with the robot as well. I'm going to skip this since we're short on time, but all of this is kind of thinking about the next interaction paradigm for the generation of computing that's situated in our physical spaces. I think AR and XR in general offer an interesting paradigm for interaction. Just want to thank my collaborators and students in my lab, and I think we're at time. but happy to answer questions if there is any time left.